Does curvature have units at any time or anything?
Well,
Is it the length, like arc length stuff?
this is a good question. So if, I believe it does. Yeah, if we look at curvature definition, so this is magnitude of R prime crossed with R double prime.
Could you zoom out or
Well,
what's that?
sort of.
Okay.
Yeah. Okay, so, and then this is over R prime of T cubed. Okay. For me to be able to get units, I need to have something to start with. So, if I started with R of T being position, so say it's something like in centimeters. And T, let's say, is in seconds. The units of R prime of T are going to be
Centimeters a second?
centimeters per second. And these are units that correspond to the I, J, and K. Guys, the units of the second derivative would be
70%.
yeah, centimeters per second, or that just gets shorthanded, centimeters per second squared. Okay. Now, what would be the units of R prime crossed with R double prime? That's a bit trickier. Okay. So, let's see if we can figure it out. I'm not going to use a specific function here, but when we go to put in our units, they're going to be centimeters per second, centimeters per second, centimeters per second for my R prime, and my R double prime, that's going to be centimeters per second squared all the way across. So when you go to get the components, I'm going to get centimeters per second multiplying centimeters per second squared. Okay, and then I will do that all the way through here. So this means that the units that I'm going to get for R prime crossed with R double prime, those are going to be centimeters squared per second cubed. Okay? You go to take magnitude, you square each of these guys and add them up, and then take square root. That's going to also be the magnitude units. So if I did this, I would have these units. Now, in the bottom here, I would have R prime, which is centimeters per second. Magnitude would be centimeters per second, and then we would cube. So in this case, K would have units in the numerator of centimeters squared per seconds cubed over centimeters cubed seconds cubed. Okay, which you unwind the algebra here, that's going to give you centimeters. So units of curvature apparently are going to be in centimeters. Okay. I don't know that I've ever sat there and worked it out, but this is exactly how you go through working it out.
Is it centimeters or 1 over centimeters?
Pardon me?
Is it centimeters or 1 over centimeters?
Oh, it's reciprocal centimeters. Yeah, because that's coming up as a reciprocal. Thank you. So, reciprocal centimeters. My goodness, there. I don't know if I find this annoying or not, because this is gonna tell me that curvature is somehow tied into the units that I use, and I guess that makes sense.
Kind of makes sense, yeah.
Pardon me?
I said that does kind of make sense. It'd be like, I'd imagine that it would be something like radians per centimeter or something like that, but
Well, there are definitions of curvature that actually will take a look at the rate of change in the angle. They're, these things are not coming down from God or something. I want to come up with some way to measure this, and I need it to have certain properties. So the radians, that is a different way of measuring it. Okay? You want to get a really nasty taste of some very difficult math. Differential geometry is where a lot of this is coming from. Good complicated stuff. Okay. One thing, one thing I mentioned last time was this formula, which takes a look at the components of the tangential and normal vectors. You turn the pages in the book and you get alternate formulas to compute these components. These are vector formulas. They're probably easier to compute with. But like a lot of things that are easy to compute with, you don't get as much insight. And so here, you may not have the insight, you may not have the ease of computation, but you will get that insight as to how changes in speed and curvature affect the normal and tangential components of acceleration. So I wanted to make sure that over here you see that these are available. Is that blurry? Look better? Okay, so these are going to be easier to compute with, but you're not going to get the insight. So relative to a test, I will provide you with both formulas. The understanding, though, is going to come from this guy that we ran through last time. Okay? So it's manipulation. I don't think there's a lot to show in terms of why these formulas work out, but it's being able to read the formulas that becomes important. Okay. this is going to be one of the places that I speed up. So there's just a little bit left in 13.5. And I think it's an important section, but I am going to do it very lightly. So this is the very end of section 13.5. Okay. So in the end of section 13.5, they are starting with R of t, which is giving position at time t. They differentiate it, and that's going to give you velocity. You take the magnitude of velocity, so that R prime I can call V of t. And if you take the magnitude of velocity, you get speed. And a lot of times you'll see that in text material, they'll write that with the same letter, V, but it's not a vector, so it's interpreted to be the magnitude of the vector, the magnitude of the velocity. So you'll see that. And acceleration is going to come by differentiating the velocity vector once or the position vector twice. All right, you have to keep in mind that speed can be constant. Without having a zero acceleration. And this is the primary difference between the Calc 1 and 2 and this. And it's because we're dealing with motion in more than one direction. And consequently, speed is only part of the understanding of velocity. You also have direction. And so if speed is constant, but acceleration is not zero, that's because you've got a change in direction. Okay? And the easiest example is to look at motion around a circle. So if I should let R of t equal, say this is a circle of radius 4, if I do this, let R of t equal 4 cosine of t in the I direction plus 4 sine of t in the j. Oops, sorry about k. J. You can check that the speed at which we move around this circle is going to be so for whatever my units are. So say if position, if this is giving me position in centimeters at time t seconds, then my speed's going to be centimeters per second. So to get your velocity out, you differentiate this one time. You take the magnitude, you get a velocity. Okay? And one would notice here that speed is definitely constant in this instance. But so my V is minus 4 cosine of t, excuse me, minus 4 sine of t, and then for cosine of t, acceleration would then be minus 4 cosine of t minus 4 sine of t. And in particular, acceleration is not the zero vector, although speed is constant. If at a particular juncture you take a look at R, so this guy right here is R of t. This is moving counterclockwise. If I go to put in R prime, it's tangential. And has got the same magnitude as R, so same length. So this would be my R prime. Where is A of t?
Inward.
Yeah, it's a multiple of R, and it's the negative multiple, so it's gonna go this way, back in. I mean, I should do it superimposed. That's hard to draw. Okay? Now, what I'm intuitively seeing here is that acceleration is entirely in the normal direction, and the comment is going to be, if you look at this formula, for acceleration, if the speed is constant, then the derivative of the speed is 0. And therefore, the tangential component of acceleration is non-existent. All of the acceleration is in the normal direction. And that's, this is just kind of a specific example of this. So we have something with constant speed, but the acceleration is clearly not the zero vector. Okay? Now, what you get at the very end of this section that I hate to skip over this, but you will get problems that look like this. So a bullet's fired from the ground at a certain angle. What's the initial speed of the bullet in order to hit a target located so and so far away? The thing you have to be careful with here is that your functions are describing motion in more than one direction. So just to give you guys somewhat of a flavor, if I have a path described by some function R of t, so let's make this two-dimensional to keep this fairly easy. So let's say this path goes up and comes down. If I ask when is the height maximized? This is somewhat of an old problem, but it's being framed in a slightly different context. So, what would I need to worry about solving here?
R prime equals 0.
Not necessarily, because what's R prime? It's velocity. But velocity is not necessarily 0 at this point.
Is it the slope of our prime?
Well, slope in the sense of tangent, I mean, you're on the right track. I mean, if I told you in Calc 1, if I said S of t is the height of an object, when is it maximized? Then yeah, you're gonna go to S prime of t equal to 0 and solve it, get the critical value out. But the problem here is that velocity at this point has got two parts to it. It's got a direction and a magnitude. So if I'm looking for when this is at a maximum, when the height is at a maximum, which part of R am I really looking at?
Why?
The Y component. So what I would be looking for here is the critical value of Y of t. In other words, I would set Y prime of t equal to 0. If I ask when does it hit the ground, in this context, it's going to hit the ground when the height is 0. But in this context, it hits the ground when,
X of t is
X.
X. No.
well, think about your coordinates.
On Y.
When Y of t is 0.
Y of t is 0. And then, you know, I could say, how far from this point did the object travel? And then it's going to be an issue of taking this time and plugging it in for x. Okay? So there's a number of problems here, and they take a little bit of time to run through just to make sure. There are also situations where you're given acceleration, and you have to integrate backwards to get velocity and position, and you will have constants of integration that correspond to initial position and initial velocity. So, I mean, they take a little bit of time to run through, but I don't think, well, I mean, we're just really slammed with time, so this is going to be one section, or this part of this section, that I'm going to leave alone, okay? And if for some weird reason we have time at the end, I'll come back and deal with it. Section 13.6 deals with planetary motion. We're not supposed to cover that. God knows we're not. I mean, you know, I don't normally have time to do things that we don't have to do, so definitely not going to do it now. So this moves us into dealing with the beginning of chapter 14. Okay, so chapter 14 is going to deal with functions of more than one variable. Example, I can define f of xy to be x squared plus 3y squared. I can define g of x, y, z to be x squared plus 3x, y, z plus e to the z. All right, as a contrast, let me observe that in really through Calc 2, you start in, I guess, pre-calculus defining functions. You have a function like f of t, you tell it to map t to t squared. F here takes a real number and maps it to another real number. We dealt with vector value functions. This is an example of a vector valued function. This is a function which starts with a real number and maps it to a vector. But that vector can also be thought of as being a point in 2 space or 3 space. Okay. What we're now looking at up above are functions which take an ordered pair, for instance, which I'll write R2, and map it to one-dimensional space. Or the example down below of G, which is taking an ordered 3-tuple and mapping it to one-dimensional space. There are certain restrictions here. We don't deal with functions starting in 4 dimensions or 5 dimensions, etc. That's purely an artificial restriction. There's no need to stop at the 3 dimensions. Similarly, I can think of these vectors as being embedded in 4 space or 5-dimensional space, whatever. Okay? What we are not doing, the most general, would be a function that takes you from n dimensions into m dimensions, where n and m can be any integers, positive integers. This is the most general way in which you can define functions. They don't have to start with a real number and map to something in 2 or 3 space. They don't have to start in 2 or 3 dimensions and map to real numbers. The calculus here is more complicated, mostly because of bookkeeping, trying to keep track of everything. We don't do this. So what we are going to look at are these two scenarios. So if, for instance, I say f of xy is x squared plus 3y squared, and I said what is f of -2 4, I mean, this is going to be 4 plus 3 times 16, which is what, 52. I mean, there's nothing fancy going on. One can look at the domain of these functions. The domains are in 2 or 3-dimensional space. So you have an old problem of f of x is 1 over x, and this is not defined when x is 0. Well, functions of more than one variable get to be potentially more complicated. So if I have f of xy equaling 1 over x squared plus y squared, and g of xy equals 1 over x times y, in neither case can we divide by 0, but in this case, f is not defined at the origin. Every other xy, it's defined at. Okay? But what about g? It's also not defined at the origin, but it's also not defined a whole bunch of other places.
0, 1, 1, 0.
Any axis, any point on the x or the y axis, it's not going to be defined at, because that's going to throw a 0 in the bottom. So it's not defined on either the x-axis or the y-axis. So you get these issues cropping up. Is that clear? If we're on the x-axis, that would mean that the y-coordinate is 0. If we're on the y-axis, it's going to mean x is 0. So I don't need them both to be 0 to bring up this issue. Okay? Okay. So these are going to be the types of functions we deal with. First issue is visualizing these functions.